My name is Dr. Ahmath. In this video, we are going to discuss about interaction of a light with a matter. And in particular, we are going to discuss about so-called BeerLamber law. Well, actually, the interaction of a light with a matter was an interesting topic for many scientists for many years. And in the beginning of the 18th century, Isaac Newton has figured out that actually the white color is nothing else as a combination of the many other colors. And he's obtained this through an experiment when the light, the white light, was dispersed into the many colors when it passes through a prism. So, well, actually, the exact graph which shows us what basically the white light is consists of is called the spectrum of the light. Well, the spectrum is the Latin word which means the appearance, and the spectrum is obtained when the light is broken into the many colors by their wavelengths. Well, let's look how exactly the experiment of the Newton was done. So let's say I've got the prism, which is made by the three triangles on the top and one square bases. And whenever the white light was passing through this prism, it was broken into the many colors. So in the beginning, people thought that actually the prism is creating the light. But later on, it was proven by Newton that actually it is not creating the colors. It is actually breaking the white color into the many other colors. And we can understand this from this perspective. So let's assume in a moment that the white color is not just one color. It is actually the combination or composition of many other colors. And it is going to be made up by the red, yellow, green, and blue colors, for example. Whenever the red color is going to interact with a prism, it is going to bend a little bit. But whenever the yellow color is going to interact with a prism, it's going to be bending more. The green color is going to bend even more, and the blue color is going to bend at maximum. So this is how exactly the light is going to disperse. So here in the beginning, so all of the lights are coming together, and we can see this as a white because the composition is going to give us the white color. And here we are going to see all of these lights or all of these colors at the separate lines because they have bended differently. And the reason why they bended differently is because of their properties. So the light consists of the photons, which are moving as waves. And depending on their wavelengths or depending on their frequencies, they are going to bend or they are going to be different from each other. And consequently, they are going to bend differently whenever they are going to be passing through one matter into another matter. So essentially, the light consists of the photon, which is moving as the waves, and the distance between the two peaks is actually called the wavelength lambda. And we can see here that for the red one, it is going to be 600 nanometers. For the yellow one, it's going to be 550. For the green one, it's 500. And for the blue one, it's 400 nanometers. And actually, the wavelength of the red color is 1.5 times more than the wavelengths of the blue. But actually, the frequency, which is more important, or which is also important property of the waves, is the number of the oscillations per second, which is going to be inversely proportional to the wavelengths. So essentially, the frequency of the blue color is going to be more than the frequency of the red color. So there are different types of the interactions of the light with the matter. So whenever the light is passing through a sample, it may be simply transmitted through the sample. It may be scattered out from the sample, or it can be absorbed. So but we can just detect the light which is transmitted or which is scattered out and understand what is this matter. What is this matter? And spectroscopy actually is the study of the interaction of the light with the matter. So by just understanding how much light has been transmitted, absorbed, and scattered, we can understand what is this matter or what is this sample. And quantitative law, which basically shows us that how much light has been transmitted and its dependency between the concentration of a sample and some material coefficients, and the length of the matter was explained by August Beer in 1853, and he stated an empirical law was the mathematical formula which shows all of these dependencies. So let's see how this law is working and what does this law is status. So let's say I've got a sample, and the sample is going to interact with some light with a certain intensity, with the incident intensity. So you can understand the intensity as simply the number of the photons per 1 centimeter square per second. So let's assume that if you've got a small square with 1 centimeter to 1 centimeter, and if there are 5 photons are passing through this square in 1 second, then the intensity is going to be equal to the 5 units per centimeter square per second. So this is essentially what does this intensity means. And after the interaction of the light with a sample, the intensity is obviously going to decrease because some light can be absorbed, some light can be scattered out. And let's denote this intensity after the interaction as I. And the BeerLamber law tells us exact law of how we can obtain the I from the I0 depending on the material coefficients and depending on the concentration of a sample and depending on the length of a sample. So we are going to denote the ratio of the I to the I0 as something which is called the transmittance. For example, if the intensity in the beginning was consist of 1,000 photons, and then just after it passes through, it consists of the 300 photons, then the transmittance is obviously going to be equal to the 30%, right? Because you are going to simply divide 300 to the 1,000 and you're going to obtain the 30%. This is what does it mean, the transmittance. And the BeerLamber law tells us that this transmittance is actually equal to the 10 in the power of minus epsilon times the C times the L, where epsilon is the material coefficient, which basically depends on what is the sample, right? It is called as molar absorption coefficient, and its units are liters per centimeter per mole. And a concentration is actually, you can understand the number of the molecules per sample, and it is going to be measured by mole per liter. And L is the length of your sample, so what distance the light should pass through this sample. And there is one more thing which is explained also by the BeerLamber law, which is the absorbance, which is actually the logarithm of the transmittance in the base of 10. So let's solve a problem. So a radiation of a wavelength 280 nanometer passes through 0.1 centimeter of a solution that contains the amino acid tryptophan, which is at the concentration of 0.5 millimole per liter. The light intensity is reduced to 54% of its initial value, and what we need to do is we need to calculate the absorbance and the molar absorption coefficient of the tryptophan at the 280 nanometers. Well, let's assume that I've got a sample of tryptophan and the light was a certain intensity. I don't know why. I'm just going to denote this as just 100% of the intensity. It's going to be reduced as a 54% of its initial value. If, for example, the incident intensity is 1,000, then you can imagine that the intensity after it passes through the sample is going to be 540. It is also given that a concentration is equal to 0.5 millimole. Milli is 10 in the power of minus 3. So this is milli, which is 10 in the power of minus 3. And the length of a sample is equal to 0.1 centimeter. So what we need to do is actually we need to calculate the absorbance and also the molar absorption coefficient. So please note that the transmittance, which is simply the ratio of the I to the I0, is equal to 0.54 simply, and this is given from the problem. So you need to be always careful with what does the problem states, and if it says to you that this is 0.54 of its initial value, then obviously you can just calculate you can take the transmittance as 0.54. But sometimes you might be given that 54% has been absorbed or something like this. So in that case, you need to be careful with the description of the problem. So far, we've defined all of the variables to our formulas, and we are ready to do the calculations. So first of all, I'm just going to do the calculations of the absorbance, which is the minus log of the base 10 of the transmittance, right? So I divided as I0 is nothing else as the transmittance, which is going to be equal to minus the logarithm of the base 10. And if you remember, the I was 54%, and I0, we took it as 100%, right? And if you take the log of 0.54 minus log of base 10 of 0.54 using a calculator and multiply this as a minus, you are going to obtain 0.27 roughly for the absorbance. Well, that's going to be the value of the absorbance. And now we need to calculate the epsilon from this formula. So molar concentration, molar absorbance coefficient for a certain material, for the tryptophan, can be calculated from here. So what I'm going to do is, I know the transmittance, right? And I know the C, I know the L, and I don't know the epsilon, and I can find this epsilon by just taking the log of base 10 from both of the sides. So let's do this. If I take the log of base 10 of this side, I to the I0 on the left-hand side, I will just obtain this formula. And on the left-hand side, on the right-hand side, so this log base of 10 in the power of minus epsilon, C, and L is going to help me to cancel this 10 in the base of the exponent. Well, on the right-hand side, I will have minus epsilon times C times the L. On the left-hand side, I've got just simply the negative of the absorbance, right? Because minus log of base 10 of the I to the I0 is nothing else as the absorbance, which is going to be equal to the minus absorbance. So from here, we can find that the epsilon is going to be equal to absorbance divided to the concentration times the length. And I'm just going to put all of the numbers together. Well, it's going to be 0.27 divided as the concentration is 0.5 millimole minus 3 times the mole per liter times the 0.1 centimeters. So please note that you need to always try to write down the units in order to make sure that you're doing all of the calculations correctly. And if you put all of these numbers into the calculator, you're going to obtain that this is equal to the 5.35 times 10 to the power of 3 times to the liter times to the liter times to the mole in the power of minus 1 times to the centimeter in the power of minus 1 liters per mole per centimeter. Well, that's going to be the value of the epsilon, or of the molar absorption coefficient for the tryptophan. So in the second problem, let's assume that the sample now should pass through the light should pass through the sample, which is now 2 centimeters, 0.2 centimeters, not 0.1 centimeter. And what we need to calculate is what is going to be the intensity after the light passes through this sample. Well, I'm just going to use the formula. So I is going to be equal to I0 times the 10 in the power of minus epsilon, C, and L. So this is actually can be obtained from the combination of these two formulas for the transmittance, and from the formula of the transmittance actually. If you remember, transmittance was I divided as I0 is equal to the 10 in the power of minus epsilon, C, and L. And if you just look to this part of this formula, is nothing else as this formula, which is obtained by multiplying both of the sides of that equation to the I0. I know actually everything in this formula, and I can just substitute everything and calculate this straightforwardly. So the I0, actually probably I needed to calculate the transmittance. Okay, so I needed to calculate the I divided as I0. So let's calculate I divided as I0, because it is difficult for us to know what is the I, because we don't know what is I0, exact value of the I0, right? So it's going to be 10 in the power of minus epsilon, C, and L. It's going to be 10 in the power of minus 5.35 times 10 in the power of 3 times concentration is going to be equal to 0.5 millimole times 10 in the power of minus 3, right? times to the length, which is equal to the 0.2. So if you would write down the units, actually, it would be the units of this term is going to be the liters per mole per liter. And the units of the concentration, actually, it's mole per liter. And the units for the length is equal to the centimeters, right? So probably here it's going to be centimeters, sorry. And you can see here that all of these units are going to beautifully cancel out each other. So it's going to be liter per, is going to be canceled with the liter, and the mole is going to be canceled with the mole, and a centimeter is going to be canceled out with the centimeter, which basically indicates that we're doing all of the calculations correctly. So this is very important that you put all of the units whenever you do the calculations in order to make sure that you're doing everything correctly. So now if I would just put everything down into the formula, the transmittance is going to be equal to the 10 in the power of and 10 in the power of minus 0.535. And if you use a calculator and do the calculations, you're going to obtain that this is going to be equal to 0.29. Well, it means that the I here is going to be 29% of the initial intensity of the light. So this is the BeerLamber law, which is basically one formula, this formula essentially, right? And two definitions. So one definition is about the transmittance, which is the ratio of the I to I0, and the absorbance, which is the logarithm of the negative logarithm of the transmittance. Well, this is what I wanted to discuss with you today. Thank you very much. I hope that this was very helpful for you.